let us discuss choice of solvent and solvent effects. In UV spectroscopy, the choice of solvent significantly impacts the resulting spectrum, influencing absorption peak positions and intensities. Solvent effects arise from interactions between solvent and solute, particularly due to the solvent's polarity. The choice of solvent significantly impacts UV spectroscopy readings by altering absorption peak position and intensities due to phenomena like solvent effects. Polar solvents typically cause red shifts, while non-polar solvents lead to blue shifts, and solvent-solute interactions can affect the molar absorptivity. The factors affecting the choice of solvent are polarity, solubility, volatility, and safety. The polarity of the solvent is a crucial factor in the extraction process. By understanding and carefully considering the solvent effects, researchers can obtain more accurate and meaningful data from UV spectroscopy. In UV spectroscopy, the choice of solvent is crucial because it can significantly influence the absorption spectrum of the analyte. Solvents should be chosen to be transparent in the visible region, dissolve the analyte well, and have minimal interaction with the analyte, ideally being nonpolar. Common choices include water, methanol, ethanol, and hexane. The choice of solvents significantly impacts UV spectroscopy readings by altering absorption peak position and intensities due to phenomena like solvent effects. Polar solvents typically cause red shifts, while non-polar solvents lead to blue shifts, and solvent-solute interactions can affect molar absorptivity. Although solvents should be in principle optically transparent, most of the solvents absorb significant amount of light, especially in the UV regions of electromagnetic spectrum. Therefore, one should choose a solvent that allows optimal transmission of the light in the wavelength range of interest. Solvent choice can significantly affect the absorption spectrum in UV spectroscopy by altering peak positions and intensities. In UV spectroscopy, the choice of solvent is crucial as it can influence the absorption spectrum in several ways. In UV spectroscopy, several solvents are commonly used, including water, ethanol, methanol, and acetometry. The choice of solvent depends on the analyte being studied and the specific requirements of the experiment. For example, water is suitable for polar or ionic compounds, while organic solvents like ethanol, methanol are used for nonpolar or less soluble compounds. And the polar components will show red shift, whereas non-polar components will show blue shifts. Choice of solvents. A solvent is a liquid that dissolves another solid or liquid or gaseous solute, resulting in a solution at a specified temperature. It should not itself absorb radiations in the region under investigation. It should not less be polar so that it has minimum interaction with the solute molecules. It should not be less polar, so B is missing here. It should not be less polar so that it has minimum interaction with the solute molecules. A drug may show a varied spectrum at particular wavelength in particular condition, but shall absorb partially at the same wavelength in another conditions. The choice of the solvent can significantly affect the absorption spectrum in UV spectroscopy by altering peak positions and intensities. This is because the solvent can interact with the solute, changing its molar absorptivity. For example, Hydrogen bonding between the solvent and solute can increase the intensity of absorption peaks, whereas solvents which do not form hydrogen bonds with the solute can decrease the intensity of absorption peaks. The solvent should be transparent to UV light in the region in which the sample's absorption peaks are likely to occur. The solvent's polarity and how it interacts with the solute's chromophore can affect the spectrum. Alcohols and water can form hydrogen bonds with the solute, which can shift the absorption bands of polar molecules. A nonpolar solvent does not form hydrogen bond with the solute, so the spectrum of the solute is similar to gaseous state. In polar solvent, hydrogen bonding can make the fine structure disappear. Polarity plays an important role in the position and intensity of absorption maximum of a particular chromophore. In the case of nonpolar solvents, for example, iodine solution, purple in color, the absorption maximum occurs at almost the same wavelength as in iodine vapor, around 5180 angstrom. Whereas in the case of polar solvents, a brownish color is obtained instead of purple color because the absorption occurs at shorter wavelengths. In UV spectroscopy, the choice of solvent is crucial as it can influence the absorption spectrum in many ways. Firstly, the solvent can shift the positions of absorption peaks, a phenomenon known as solvent shift. This occurs because different solvents can alter peaks to shift to longer or shorter wavelengths. Most commonly, 95% ethanol. It should be cheap, have good dissolving power, and does not disturb radiation above 210 nanometer. Solvents used in preparation of sample for UV spectra can be of two types. One is polar solvents, the other one is non-polar solvents. Polar solvents. Polar solvents like ethyl alcohol have electronegative atom with lone pair of electrons or non-bonding electrons. This non-bonding electron can form a solute-solvent complexes through hydrogen bonding. Hence, if the lone pair of electrons is in conjugation with the chromophore group, the lambda max increases to higher values. Also, it is seen that the polar solvents or solvents interacting with the sample molecules diminishes the hydrogen structure of UV spectra. That means peaks become broad. For instance, polar solvents often cause a redshift, shifting towards longer wavelength, while non-polar solvents cause a blue shift, shifting towards the shorter wavelengths. Non-polar solvents. Non-polar solvents do not form hydrogen bond with solute, so fine structure is often observed. This is called a hyperfine peak structure. We can see that there are three peaks in the isooctane, but in ethanol, all the peaks are overlapping. Hyperfine structure is almost absent. It is shown in the figure. The changes in spectrum are due to nature of the solvent, nature of the absorption band, and nature of solute. Nature of solvent. Most commonly used solvent is 90% ethanol. It is the best solvent as it is very cheap. It has good dissolving power. It does not absorb radiations above 210 nanometers. In choosing a solvent, consideration must be given not only to its transparency but also to its possible effects on absorbing system. Benzene, chloroform, carbon tetrachloride cannot be used because they absorb in the range 240 to 280 nanometer. It should not itself absorb radiations in the region under investigation. It should be less polar so that it has minimum interaction with the solute molecules. So some examples of solvents and the respective wavelengths are given in the table. Solvents are water, methanol, ethanol, ether, chloroform, carbon tetrachloride, and cyclohexane. And for water, the corresponding wavelength is nothing but 205. So methanol, it is 210 and ethanol is 210. Ether also has the same wavelength, 210 nanometer. Chloroform little bit higher, 245 nanometer. And carbon tetrachloride, 265 nanometer. And the last one, cyclohexane, 210 nanometer. Important factors of solvent selection. Optical transparency. The solvent should not absorb light in the wavelength range of interest for the analyte. Water, for example, is a good choice of UV spectroscopy because it does not absorb light in that region. Solubility. The solvent must dissolve the analyte adequately to allow for accurate measurements. Interaction with the analyte. Ideally, the solvent should have minimal interaction with the analyte, especially in the excited state. Non-polar solvents like hexane tend to have less interaction than polar solvents like ethanol. Purity. The solvent should be of high impurity to avoid interfering with the analyte's absorption spectrum. Commonly used solvents. Water. A polar solvent that is transparent in the UV visible region, making it a good choice for many analytes. Ethanol. A versatile solvent that dissolves a wide range of compounds and is generally transparent in the UV visible region above 210 nanometer. Hexane, a nonpolar solvent that can be useful for studying analytes with less interaction with the solvent. Methanol, another polar solvent that is commonly used in UV visible spectroscopy. Other options. Other solvents such as acetonitrile, dimethyl formoate, and dimethyl sulfoxide can also be used depending on the specific analyte and the research question. Impact of solvent on the spectrum. The solvent can affect the absorption spectrum by shifting the absorption peak. Polar solvents can cause the absorption peak to shift to longer wavelengths, redshift, or shorter wavelengths, blue shift. Changing the absorption intensity. Solvent polarity can also affect the intensity of the absorption peak, altering the shape of the band. Solvent interactions can change the shape of the absorption band. In summary, selecting the appropriate solvent for UV visible spectroscopy involves considering factors like transparency, solubility, interaction with the analyte, and the desired effect on the spectrum. Three types of solvents. Three main types of solvents are nonpolar, polar aprotic, and polar protic. Nonpolar solvents like hexane have molecules with little to no dipole moments. Polar aprotic solvents such as acetone have a high polarity but do not have acidic hydrogens. Polar protic solvents like water have high polarity and can act as proton donors. Nonpolar solvents. These solvents are composed of molecules in which the atoms within are bonded with similar electronegativity, resulting in a lack of strong dipole moments. Examples include hexane and benzene. Polar aprotic solvents. These solvents are characterized by high polarity and a lack of acidic hydrogens. They cannot act as proton donors during hydrogen bonding. Examples include acetone, dimethyl sulfoxide. Polar protic solvents. These solvents have both high polarity and acidic hydrogens, allowing them to act as proton donors in hydrogen bonding. Examples include water and alcohols like methanol and ethanol. Importance of solvent choice. The choice of solvent is crucial in UV spectroscopy. A suitable solvent should be transparent in the region of interest, solubilize the solute effectively, and minimally interfere with the solute's absorption. Ethanol is a solvent of choice in UV spectroscopy because ethanol is polar solvent, has ability to form hydrogen bonds. It is solvent. and also its UV-based absorptions cutoff wavelength region is very low, around 205 nanometer. Therefore, it is used widely in UV-based spectroscopy. Although solvents should be in principle optically transparent, most of the solvents absorb significant amount of light, especially in the UV regions of electromagnetic spectrum. Therefore, one should choose a solvent that allows optimal transmission of the light in the wavelength range of interest. The effect of solvent. The absorption spectrum of a pharmaceutical substance depends partially upon the solvent that has been employed to solubilize the substance. A drug may absorb a maximum of radiant energy at a particular wavelength in one solvent, but shall absorb practically little at the same wavelength in another solvent. For example, we just take the absorption spectrum of iodine in a nonpolar and polar solvent. So wavelength which lies between 500 and 750 micron, so which is nothing but nonpolar solvent. And this wavelength in this range 250 to 500, and this is for C2H5OH. And this is nothing but polar solvent. And this is for the polar example for the polar solvent is this C2H5OH, and non-polar solvent is chloroform. Salient feature of solvent effect. The spectrum of iodine in a non-polar solvent like CHCl3 is found to be distinctly different purple to the naked eye when the same is compared to the polar solvent such as C2H5OH, brownish to the naked eye. Solvent effects. Solvent effects in UV spectroscopy refer to the influence of the surrounding solvent on the UV-based absorption spectrum of a solute. These effects can alter the position, intensity, shape of the absorption peaks. Solvents can shift the absorption maximum towards a longer wavelength, bathochromic shift or red shift, or shorter wavelengths, hypsochromic shift or blue shift. This is due to interactions between the solute and solvent molecules, including changes in polarity, hydrogen bonding, and other specific interactions. Polar solvents can shift absorption peaks towards shorter wavelengths, blue shift or hypsochromic shift, or longer wavelengths, red shift or bathochromic shift, depending on the interaction between solvent and the chromophore. Non-polar solvents generally exhibit less of an effect on absorption peak positions. A solvent exerts a profound influence on the quality and shape of the spectrum. The absorption spectrum of pharmaceutical substance depends practically upon the solvent that has to be employed to solubilize the substance. A drug may absorb a maximum radiation energy at particular wavelength in one solvent, but shall absorb partially at the same wavelength in another solvent. For example, acetone in N-hexane. So lambda maximum is observed at 279 nanometer, whereas acetone in water, lambda max is observed at 264 nanometer. The position and intensity of an absorption band may shift when the spectrum is recorded in different solvents. A dilute example solution is prepared for analysis. Most commonly used solvent is ethanol, which is nothing but 90%, 95%. A spectrum normally shows the appreciable changes with varying pH when an ionizable part is present in the molecule and thereby constitutes part of the chromophore structure. Position as well as intensity of absorption maxima get shifted for a particular chromophore by changing the polarity of solvent. By increasing polarity of solvents, dienes, conjugated hydrocarbons, and there is no shift. Basic requirements. Solvent should not absorb UV light in the region in which our sample is absorbing, else peaks will overlap. Solvents should not interact chemically with the sample molecules. Even small hydrogen bonds affect the peak position and its width. If possible, we should avoid the use of polar solvents as they interact with the chromophoric groups. Solvatochromism. The solvent effect in spectroscopy refers to the influence of a solvent on the position, intensity, and shape of the absorption bands in a solute spectrum. This effect is particularly noticeable in UV spectroscopy, in which the interaction between the solute and the solvent can shift absorption peaks towards longer or shorter wavelengths, a phenomenon known as solvatochromism. It is the ability of a chemical substance to change the color due to change in solvent polarity. The sign of solvatochromism depends on the difference in the dipole moment of the ground and the excited state of the chromophore. The presence of specific and non-specific interactions between the solvent and solute molecule is responsible for the change in the molecular geometry, electronic structure, and dipole moment of solute. These solute-solvent interactions may affect the solute electronic absorption spectrum. This phenomenon is known as solvatochromism. The phenomenon in which the absorption spectrum of a solute changes with varying solvent polarity is known as solvatochromism. It is a valuable tool for studying solute-solvent interactions and understanding the nature of electronic transitions. Solvatochromism refers the shift in the absorption spectrum of a molecule when its environment, that is solvent, changes. Mechanism. This phenomenon arises because different solvents can stabilize the ground and excited electronic states of a molecule to varying degrees. If the excited state is more stabilized in a polar solvent than the ground state, a redshift, pathochromic, will occur and vice versa. Solvatochromic effect in UV spectroscopy. The solvatochromic effect in UV spectroscopy refers the change in a molecule's absorption spectrum when it is dissolved in different solvents. This change is due to varying solvation energies between the ground and excited states of the molecule in different solvents. Essentially, the molecule's color and thus its absorption spectrum shifts when the solvent changes, indicating a change in the solute's electronic structure, polarity. Polar solvents stabilize solar excited states, leading to a redshift, pathochromic. Non-polar solvents, it provides less stabilization, potentially leading to a blue shift, isochromic. Effect of solvent polarity on electronic transitions. Pi to pi transitions. In pi to pi transitions, the solvent polarity is increased. Both the ground and the excited states are generally stabilized by polar solvents, but the excited state is more strongly stabilized, leading to a redshift. The transition of polar bonds like C double bond with O but not ethylene are affected by the solvent polarity. N to pi transitions. This band undergoes blue shifts since ground state with 2 electrons receive greater stabilization than the excited state with only 1 n electron. In N to pi star transitions, the ground state is less polar than the excited state, and therefore polar solvents will stabilize the ground state more than the excited state, resulting in a blue shift. Other solvent effects. Solvent effects help in recognizing electronic transitions of the type N to pi star that essentially involve the non-bonding electrons of nitrogen and oxygen. The non-bonding electrons of nitrogen and oxygen usually interact with polar solvents that ultimately give rise to a characteristic shift to shorter wavelengths. Hydrogen bonding. Solvents capable of forming hydrogen bonds can interact with a solute, influencing the absorption spectrum. Solvent transparency. The solvent should be transparent in the region of interest to avoid interference with the sample's absorption spectrum. Examples. Pyridine. The UV absorption spectrum of pyridine shifts noticeably towards the blue when the solvent is changed from hexene, that is nonpolar, to methanol, that is polar. Coumarine 138. Absorption studies of coumarine 138 in various polar and nonpolar solvents, example cyclohexane, dioxin, acetonitrile, demonstrates the solvent effect on absorption peak positions and intensities. Factors influencing solvent effects. Solvent polarity. The primary factor influencing the shift in absorption peak positions. Polar solvents generally stabilize polar excited states, leading to a pathochromic shift. Hydrogen bonding. Interactions between the solvent and solute molecules can also influence the spectrum. Solvents capable of hydrogen bonding can interact with solutes, altering their electronic environment and absorption properties. Specific solute-solvent interactions. Non-specific interactions like dispersion forces can also influence the spectrum. Solvent transparency. The solvent itself should be transparent in the region of interest to avoid interfering with the solute's absorption. Solvent refractive index. The solvent's refractive index can also contribute to the observed spectral shifts. In summary, the solvent plays a crucial role in UV visible spectroscopy, affecting the position and intensity of absorption peaks through various mechanisms, including solvatochromism, hydrogen bonding, and solvent polarity. And choosing an appropriate solvent is essential for obtaining accurate and reliable spectral data.